Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Thanks all four of you for coming so early in the morning. It was our pleasure to have Vinay Sethi today visiting us from University of Oslo. And Vinay has done some interesting work on pub-sub systems and peer-to-peer and other interesting stuff. So over to you, Vinay.
Thank you. Hello, everyone. Thank you for showing up so early in the morning. Today, I'm going to talk about publish-subscribe systems for social interaction, mainly in social networks, the design aspects of it, the workload analysis for it, and resource provisioning for it. This is a joint work with my supervisors, Roman and Martin, and also a couple of employees from Spotify, Gunnar and Guido. So just a bit of a background about me. I'm a PhD candidate at University of Oslo in the Networks and Distributed Systems group. And my supervisors are Roman Wittenberg and Martin Vanstein. And during my PhD, I have been working on mainly publish-subscribe systems, various architectures for publish-subscribe systems like peer-to-peer, peer-assisted, and also looking into subscriber satisfaction problems, and also resource provisioning for it. During my PhD, I also got an opportunity to do research internship at Spotify. Some of the work I present here today was done during that period of time. And before I started my PhD thesis, I did master's in Max Planck Institute for Informatics in Saarbrücken, Germany. It was about identifying interesting time points in a web archive or a text archive. This was in Professor Wycombe's group, if you know. And before my master's, I also have almost 3 years of work experience as a software engineer from a company called Electronics for Imaging in India. And I also got my bachelor's before that from India as well. So I'm not sure if you're familiar with publish-subscribe systems. In short, it's pub-sub. It's a communication paradigm. There are publishers and subscribers. And there is a middleware which acts as a connecting overlay or a bunch of brokers which are matching the subscriptions against publications and delivering it to the subscribers. So basically, there are subscribers sending subscriptions to the middleware, and there are publishers publishing relevant publications, and it's the job of the middleware to deliver those notifications to the subscribers. There are typically two types of matching, like topic-based matching, where there are discrete topics against the publication, which publications are matched and delivered. There is also attributes-based matching, which is more commonly known as content-based pub-sub. So there are several industry standards and applications which are out there. One most popular example is even RSS feed distribution can be considered as a pub-sub application. And there are standards from OMG's real-time data dissemination service. There are also many topic-based pub-sub systems out there used in the industry. There is TIBCO's Rendezvous pub-sub, and Google's internal pub-sub for synchronizing data across their data centers called Goops. And finally, during my thesis, I found out that pub-sub also plays an important role in delivering social interaction events. And this is especially true for Spotify. So I'm not sure if you're familiar with Spotify. If not, it's an on-demand music streaming service. It has a large collection of music tracks with over 20 million tracks. It's available in more than 55 countries across the world. And there are more than 25 million active users using it. It's a fast and legal way of listening to music. And last but not the least, the little-known feature of Spotify is it also allows social interaction among its users. So we'll see in detail what I mean by social interaction. So if you're familiar with Spotify client, And in the bottom right corner, you can see a real-time feed of what your friends are listening to and what your favorite artists are doing, like if they released an album or if they created a playlist of their favorite songs, you get notified instantly. But one thing I want to emphasize here is that this event feed is of fixed number of events here. So if there are more events being generated at any given point of time, the user will not be able to see those extra events, and they're just discarded. So let me go more in detail into what kind of social interaction I'm talking about and how it maps to PubSub. So there is Spotify user, and who can follow other Spotify users or imported users from Facebook. When that happens, whenever the friend listens to a music track or creates a playlist or updates a playlist, the user gets notified about it. And there are also artists in Spotify. You can follow artists. And as I said, when they release an album or a music track, the users get notified about it. There is also a feature in which the artist can be verified, which means the account belongs to the real artist. So whenever they listen to a music, basically their music activities are also notified. And in Spotify, there is also a concept of playlists, where you can just create a collection of music tracks into a playlist. And some of them are public, so you can search for playlists, and you can also follow them or subscribe to them. And of course, if there is an update to that, you get notified instantly about it. And finally, optionally, all the music activities of Spotify user can be also posted onto external social networks like Facebook and Twitter. So having studied PubSub for a while now, it clearly maps to a set of topics, and there is a subscriber in the middle. And for me, it looks like a very nice fit for a PubSub communication paradigm. So you can also map other social interactions out there into PubSub communication paradigm. For example, Twitter, where users follow other users. And the follow relationship, if a user follows a set of other users, we can say in PubSub terms that user subscribes to these other users. And also, conversely, you can say that if a user is being followed by other users, then the same user can be a topic. So he's being followed by, subscribed by other subscribers. So one unique thing about the PubSub for social interaction is that a user can be both a topic and a subscriber. So he can also be a publisher as well as subscriber. So I don't think I need to motivate much that the social interaction is of large scale these days. Just to give you some perspective, in Spotify, there are billions of notifications being delivered every day. And it amounts to more than 2 terabytes of data being sent into Spotify data centers and delivered back to the users. And there are millions of active users across more than 55 countries who are subscribing to these events. As I said, there are 25 million active users, and at any given point of time, more than 20% of users are subscribing to this PubSub system. And basically, Spotify has 3 data centers, 2 in Europe and 1 in North America, the last I knew. And to give you some numbers about Twitter, you probably already know, but there are more than 500 million users and more than 200 million active users. And every day they generate more than 400 million tweets, which amounts to just 12 terabytes of just the tweet data being sent and received from Twitter data centers. So such a large scale poses several challenges. One of the most important things is it demands a scalable architecture. It should be naturally scalable with the number of users. So in this regard, there is a need for decentralized solutions. And having seen examples of Twitter and Spotify where they redesigned their notification delivery systems due to increase in scale, Spotify especially wanted to explore if there are natural ways to scale social interaction naturally with number of users. So in this regard, During my PhD thesis, I worked on a paper which was published in Middleware 2012. This was about a peer-to-peer publish-subscribe system for topic-based pub subsystems, where we show that it naturally scales well with number of users. This was a gossip-based overlay to maintain the overlay, and we show that it is scalable with number of users, number of topics, and the subscription size, which is the number of topics per user, and so on. I'll not go into details of this work in this talk due to limited time, but just to give you an overview, in the overlay, we wanted to avoid any rendezvous nodes or special nodes or special peers, which could be the bottlenecks. So, and also we wanted to avoid any relay nodes, which are, for example, if a node is not subscribed to a topic, it will not be participating in forwarding the events, which it is not subscribing to. And we also show that it's a low latency delivery, and also under churn, when the nodes are joining and leaving the overlay, it performs pretty well in terms of delivery rate. So just to give you a snapshot of the result, we compared the miss ratio with Twitter and Facebook data, and we introduced the churn from Skype churn traces. And we show that it performs at least 10 times better in terms of miss ratio compared to popular PubSub system, topic-based PubSub system, Scribe, which is built on Pastry. And it also relies on the churn handling of the Pastry, and it does not do a good job of repairing the overlay when the nodes are leaving and joining. So the next challenge.
A single data center.
Sorry?
Is Poltercast in the context of a single data center?
Okay, so we addressed it in a more general peer-to-peer setting, but it can be a single data center also.
In practice, these things are likely to be. I mean, Spotify probably does run in a data center, doesn't it?
So actually, in
peer-to-peer systems, as I understand it, they're meant to run on your computer.
In Spotify case,
spare cycles and all that.
In Spotify case, we were actually looking at peer-to-peer network of the clients, of the users, because Spotify is already a peer-assisted streaming service. So there is already a peer-to-peer network existing for streaming the audio. So we wanted to explore if it's possible to exploit the same network to deliver PubSub events as well. But yeah, the Poltercast was purely peer-to-peer PubSub system, but as we'll see later in the talk, the other ideas we looked at was to actually combine these two and have a peer-assisted solution for Spotify. So the other challenge in large-scale social interaction PubSub systems is that a real lack of real-world workload. So in this regard, we got an opportunity to study the workload characteristics of Spotify PubSub, and it was published in Distributed Event-Based Systems Conference last year. I will not go into the details of the work, but I'm happy to talk to you later about it. The next challenge we wanted to look at was the distribution of workload. So this was related to the peer-assisted architecture I was talking about. So basically, instead of having all the workload being handled by the Spotify backend infrastructure for PubSub, we wanted to see identify the part of the workload which is more beneficial to the users, and offload the less beneficial workload to low capacity computing or less reliable computing like peer-to-peer network.
I thought the whole point of the first thing, which was, what did you call it, decentralized something?
Yeah.
I thought the whole point of that was exactly to spread the work out.
Yes.
So how does this differ from what you were talking about to begin with the first topic?
So in the beginning, there is no differentiation in the workload. All the workload is distributed to the peer-to-peer network.
Right.
But it's less reliable in the sense that if you rely on the computing power of the client users, then it's less reliable and
Less reliable
than being delivered by the backend infrastructure, which is dedicated for delivering the events. So in the peer-to-peer part, we didn't address any reliable delivery or any persistence, for example. But the backend infrastructure provides all that. So that's why we want to identify more important workload. I'll come to the part what I mean by more beneficial workload, and the rest can be distributed to peer-to-peer component. So to identify more beneficial workload, we worked on various satisfaction metrics for subscribers. So what makes subscribers happy, and beyond which any more delivery of events is being wasteful. So this work was recently accepted in Infocom. It is to appear later this year. So just to give you an idea here, if there are many topics being subscribed by a user, usually the kind of social interaction systems we are dealing with here, the end user is a human user who has a certain limited capacity of processing the events at any given unit of time. So let's say we have a subscriber who subscribes to two of his friends, Alice and Bob, and two celebrities, Gaga and Bieber. But all of them together produce a lot of events, which is too much to handle for the subscriber. The subscriber says that I can only handle 5 events at any given point of time. So this gives us a threshold on satisfaction for the user, and we set that to be 5, which is the processing capacity limit for the user. So having a delivery rate for each user beyond this threshold is not beneficial, but having the delivery rate below this threshold is less beneficial. It can be bad for the user because he may think that there's something wrong with the system and may suspect that some failure or something. So in this regard, we define novel satisfaction metrics where we say that each user can define a delivery rate that they want to subscribe to. And the goal is to meet these satisfaction threshold for as many subscribers as possible, and by considering other aspects like cost and resource availability.
Do you think that all events are equally good for the user, so there's no kind of prioritization?
Yeah, in this work we consider that, but you can also imagine the variations of this problem where if there is a ranking function provided between the subscribers and the topics, you can prioritize them based on the score. So I mentioned all these things that in this work we define a set of satisfaction metrics, and our goal is to select part of the workload which meets the satisfaction metric, and we also briefly provide an architecture where it can be used to offload the workload to the less reliable and cheap computing power like peer-to-peer network. So the next challenge is resource provisioning. So for example, to give you an idea, in Spotify, it was not very, they didn't have a proper tool to measure the amount of resources needed to drive the PubSub workload they had. And most of the time, they're just over-provisioning it. So
the central infrastructure, not the peer-to-peer.
Not the peer-to-peer part.
You're talking about the central infrastructure.
Yeah.
Okay.
So in this regard, we provided a tool where, given a PubSub workload, we give the amount of resources needed to meet the satisfaction of all the subscribers, or given target number of subscribers, with the same kind of satisfaction metrics I talked about earlier. And we also use pricing model from, let's say, cloud service providers like Amazon, and then we provide a tool where you can come up with a resource allocation which minimizes the monetary cost. So this was recently accepted in ICDCS. I guess this group is involved in the same track. So in the rest of the talk, I'll talk about the subscriber satisfaction problems, which is used for identifying the more beneficial and less beneficial workload and various solutions for it. And then I move on to the problem of resource allocation, cost-effective resource allocation in data center and cloud settings, and then I conclude. So coming back to the same example earlier, there's a subscriber who has a specified satisfaction metric. And now we have a limited real estate where we want to show the notifications for the subscriber, relevant to the subscribed topics, of course. You can imagine various types of ways to fill this real estate. As you mentioned, it can be ranked, so that it can be like a top K kind of delivery of events, or it can be the most recent, where you give the recency priority. Or it can also be diversity, where you can diversify. But the last one, which is the main focus in this work, is actually from the PubSub service provider's perspective, how to do it in a most cost-effective manner. Because Spotify, for example, does not consider this to be a critical infrastructure, but they still want to have this feature with minimum cost as possible. So to achieve this, we define satisfaction metrics, and the goal is to select cost-effective workload to maximize the satisfaction of the subscribers, and also allocate resources to achieve that. So in this regard, we define two satisfaction metrics. The first one is called binary satisfaction metric, where we have a subscriber, and for example, I'll explain the binary satisfaction metric with an example. With the same satisfaction threshold, which was specified in the previous example, the 5, for example. And there are several topics. And each topic has an event rate, which is the number of events per unit of time. Let's say Bob has 4 events per unit of time. And each topic also has other subscribers, of course, in addition to this subscriber in the given example. So according to the binary satisfaction metric, the goal is to now meet the delivery rate event threshold for this user, which is 5 in this case. But selecting Bob does not meet that criteria. So in the binary satisfaction metric, the user is, in this case, is not satisfied, even though it meets 4 out of 5 the requirement. But now when we include Gaga, which contributes 100% to the required threshold, and this is now, the user is now satisfied. And the second type of satisfaction metric we defined was fractional satisfaction metric, where instead of saying that a user is either satisfied or not, we give the relative value to the satisfaction. In this case, user is 80% satisfied, even though it's not 100%. But when Gaga is selected, again, 100% satisfaction is met. But one more thing I want to emphasize here is, since Gaga has 1 million other subscribers, selecting Gaga would also contribute 20% to satisfaction of 1 million other subscribers. So,
wait a minute. So their satisfaction thresholds might be different. So why 20%? And also, just because subscriber V, we let him see Gaga's stuff, doesn't mean you're making that decision for everybody else.
Yeah.
Does
so
it? Does it?
in our model, to simplify, we assume that the satisfaction metric is constant for, especially in the Spotify case. Each client has a fixed amount of events that they can receive. So, but I don't see why this cannot be changed. We can basically make it a function, and each subscriber can specify their own satisfaction metric. And yeah, in that case, the contribution is not the same, but it's per subscriber dependent. But that doesn't affect the difficulty of the problem or the solution.
You're saying selecting Gaga means that you select it for everybody?
Yes.
Isn't that a big assumption? I mean, maybe it would be better for me to, have Alison, Bob, and Bieber, and for somebody else to have Gaga and Bob.
Now you are talking about actually ranked. The same thing Christos mentioned, that if there is a priority, if we can give priorities to different events. So if there is a ranking function available, we can do that as well. And we can. I'll come to the heuristic where we look into the benefit and cost of choosing a topic, and we can adapt the benefit to include the priority that you specify or each subscriber specifies.
But for now, you're saying if you select one source of one publisher for one user, you select it for all users.
Yes.
Okay, that seems like a big assumption.
Actually, it's all users that are interested in that.
Oh, okay, yes, all interested users, yeah.
So each topic also has a cost. The cost can be modeled. It depends on the amount of resources that it requires to drive that topic or deliver publications to the subscribers of the topic. So to simplify the model, we assign it, set it to be the event rate times the number of subscribers of the topic. And now there is a capacity constraint on the backend PubSub infrastructure. Like for example, in case of Spotify, they say we have these many servers and this is the capacity they can handle. And now the goal is to select topics in such a way that we don't violate the capacity constraint, but meet the satisfaction metric of as many users as possible. So to formalize this problem, it's a ridiculous name, but in short, it's called B3M because we saw that it's similar to set multi-cover under budget and constraint problem, but in nature, it's a different problem. So we are given a set of topics and their event rates and the subscribers, and we are given a binary satisfaction metric. And we are also given a capacity constraint on the backend infrastructure. The objective here is to maximize the number of satisfied subscribers without violating the capacity constraint. And in the paper, we prove that this is NP-hard problem by reduction from densest case subgraph problem, if you're aware of it. And as a corollary, we also show that there is no polynomial time approximation scheme for this problem. So we stick to the heuristic-based solution. I'll explain the heuristic with an example. Consider, again, there are 3 topics and 2 subscribers for the purpose of example, and they both have same satisfaction threshold, which is 5 in this case. So the heuristic is to compute the contribution of each topic towards the subscriber. So in a very simplistic model, it's just the event rate, contribution of event rate towards the uncovered events, which is to meet the satisfaction of the subscriber. But
so what does uncovered mean?
So this is the threshold. For a subscriber, there is a threshold. So for example, in this case, the uncovered for both the subscribers is 5, since we have not selected any topics. So when we select the topics which meet the needs of the subscribers, the threshold of the subscribers, partially, then the uncovered decreases. And eventually, when all the satisfaction threshold is met, the uncovered becomes 0. So
so what is uncovered?
The satisfaction threshold minus the covered.
What is the cover?
When we select a topic, the event rate of the topic contributes to the cover. So for example, here...
The sum of the event rates of the selected topics.
Sorry?
The cover is the sum of the event rates of the selected topics. Okay.
So for example, if Gaga is selected here, the covered part is 3. and the uncovered part is 2 for both the subscribers. So now, for each topic, we sum up the contributions towards their subscribers. So that's why I say when we can have a benefit, we can modify the benefit to include the ranking as well. Suppose we have a separate, let's say a weight function to give ranking for each subscriber differently. Then we can compute the benefit of the topic by introducing the rank or the weight and weigh the cost against it. So, and then we compute the benefit to cost ratio. The algorithm is that we select the topics with the best benefit to cost ratio. And as we select the topics more and more, we update the benefits of affected topics which have common subscribers, because having selected a topic for a subscriber decreases the benefit for contribution from the other topics. So in this case, we have a tie. We break the ties with by choosing the topic with the most absolute benefit. In this case, it's Gaga. And when we select Gaga, now the covered part is 3 and the uncovered part is 2 for the given satisfaction threshold of 5. And one more thing I didn't mention is also there is a capacity, server capacity. And as we select more and more topics, the capacity decreases. So as we proceed with the algorithm, the benefit of, for example, Bob is now increased to 1, because if you select Bob, it completely meets the satisfaction of subscriber V1. So and then it becomes the most beneficial topic, and this is the topic which has highest benefit to cost ratio, and then we pick this topic. And finally, we also pick Bieber to meet the satisfaction of both the subscribers. In the fractional version, the problem setting is very similar, but only difference is the satisfaction metrics is a metric is a fractional satisfaction metric. But here, instead of focusing on maximizing the number of satisfied users, the objective is to maximize the cumulative fractional satisfaction for all the users. So it may be possible that none of the users are 100% satisfied, but all the users are, let's say, 90% satisfied. So the goal here is to maximize the satisfaction of as many users as possible without focusing on completely satisfying any single user. But it turns out such a small modification to the problem also changes the hardness of the problem, and it's very similar to budgeted max cover problem. And inspired by the solution for budgeted max cover problem, we also propose a greedy algorithm which gives a constant approximation ratio. So coming back to the same example as earlier, here the algorithm is similar, but the way contribution is computed for each topic is different. The only difference here is instead of looking into the uncovered events and how much the selected topic contributes to the uncovered events, we keep the denominator constant, which is the satisfaction metric, or whatever the satisfaction metric of the subscriber is. And then when we choose a topic, we see what fraction of it covers. But if it is meeting more than 100% of already required number of events, then we give a maximum of 1 to the contribution. Again, the algorithm is the same. We sum up the contributions to get the benefit of the topic, and we get a ratio of benefit to cost. And we select the topic with the best benefit to cost ratio again. In this case, we break the ties again by choosing the topic with the best absolute benefit, which is Bieber for subscriber V2. But now, the interesting thing here is that the benefit of Gaga towards subscriber V2 becomes 0, because subscriber V2 is now completely satisfied, choosing Gaga does not contribute anything to that subscriber. So this, we make an important observation here that the contribution, the benefit can only decrease. It's a property called submodularity, where if we select more and more topics and add it to a bigger and bigger set of topics, the benefit keeps decreasing. So we exploit this property of submodularity. Later I'll show that how it helps in in improving the performance of the algorithm, where we can avoid updating the benefits of all the relevant topics. So if we sort the topics according to their benefit, and then if we go on updating the topics until we see that there is no more decreasing in the benefits, then we can stop updating the benefits of the topic. This pre-termination of updating the benefits has significant improvement in the performance. So just to complete here, the next topic with the best benefit to cost ratio is Bob. And when we select Bob, in this example, it turns out there's no more capacity to choose third topic Gaga, and which leaves subscriber V1 80% satisfied and subscriber V2 100% satisfied. So let's see how these heuristics perform in practice. We use the dataset from Spotify with subscriptions and publication rates. And it was collected for 10 days from Stockholm Center. And for satisfaction threshold, we give an exponential variation of the default constraint they have in. Like I mentioned, in Spotify client, you can only see a fixed set of events, fixed number of events. And that turns out to be 25. And we give an exponential variation of this to do the sensitivity analysis. And we also set the cost of a topic, as I mentioned earlier, to be the event rate of a topic and times the number of subscribers. Basically, this is to capture the amount of resources needed to handle that topic. And we also set a capacity constraint on the back end. Instead of setting arbitrary capacity constraints, what we do is to compute the cost of all the topics in the system, in the entire workload, and then we set the capacity to be 10% of this topic, 10% of this cost, total cost. Basically, what we want to see is given 10% of resources, what is required to run the 100% of the workload, how many subscribers we can satisfy. And the goal is to offload the rest of the workload to peer-to-peer network, for example. And to compare the quality of our results, we also derive an upper bound for a given set of topics and their cost. We see that without worrying about the semantics of who subscribes to who, we can actually come up with an upper bound on how many subscribers, in theory, we can satisfy. But this is a loose upper bound. So what you see here is in the x-axis, the capacity, like at each iteration of our heuristic algorithm, we measure the number of satisfied users. And what you see in x-axis is the cost required to meet the satisfaction of a number of satisfied users. So the number of satisfied users is in y-axis. And this is up to maximum of 10% of total workload cost. So the red line is the output of our heuristic for binary satisfaction in the left side and for the fractional in the right side. And the blue line is the derived upper bound. So there are 4.9 million users in total. And in the binary satisfaction case, we are dealing with maximizing number of satisfied users. So when we look at 10% cost, then we see that there are more than 70% users satisfied, while we are only using 10% cost. But in the fractional case, the number of satisfied users does not make sense, but we look at the average satisfaction of all the users, which is the fraction we computed in the fractional satisfaction metric I defined earlier. And it turns out with only 10%, of course, we can meet 90% average satisfaction for all the users. So in the next experiments, we wanted to see how it performs in terms of running times. And we see that all the variations of the algorithms run in under 35 seconds. Here I want to show the impact of submodularity optimization I talked about earlier. And with the submodularity optimization for fractional version, we can see that it runs in under 20 seconds for all the different values of satisfaction. And it turns out for a very large satisfaction metric, it actually runs faster, because you can imagine if you set the satisfaction metric to be infinite, then we don't have to think it. We can just select all the topics, because we need all the topics to satisfy all the subscribers. So which means for large values of satisfaction metric, there is less computation to do or less iterations to update, so it runs faster compared to lower and intermediate values of satisfaction threshold. We also wanted to see how the heuristics perform when we recompute at periodic intervals with the changed workload in the, let's say, last 1 hour or so. So for this case, we divided the workload into hourly windows with 30 minutes overlap with the neighboring windows. And we wanted to measure both the running times as well as ratio to the upper bound, derived upper bound. And we see that it's pretty constant across all the windows. This is for 10 hours of time. And in terms of running time, for the fractional heuristic for the fractional version is pretty constant, around 100 milliseconds, while the solution for the binary satisfaction metric is very sensitive to the workload. This is again because of the pre-termination of updation of benefits due to submodularity that I talked about. So I switch gears and move on to the final part of my talk, which is resource allocation for PubSub to meet the satisfaction of subscribers, all the subscribers in data center and cloud settings. So in the previous work, we considered the backend infrastructure to be a single unit. But in practice, it's also hard to set a capacity constraint on this single unit. And it's also not single unit. It comprises of many servers, or in terms of cloud, it's many virtual machines. And the goal here is to find a resource allocation which minimizes the number of virtual machines required to drive this workload to meet the satisfaction of the users, and also at the same time minimize the bandwidth consumption, total bandwidth consumption for driving this workload. This bandwidth consumption I'm talking about is the inter-server bandwidth. Sometimes in case of Spotify, for example, if the PubSub servers are distributed across data centers, let's say there are subscribers connected to Spotify data centers in Europe data center and the North American data center, and there is a topic for which the subscribers are in both the places, and now we are required to replicate the events to all these subscribers, and this incurs a bandwidth overhead of replicating the publications across different data centers, or even within the same data center across many different servers. So we see that there is a trade-off between number of servers and the total bandwidth consumption. If we try to minimize the number of servers by allocating the topics to as few servers as possible, it may not necessarily be bandwidth efficient. At the same time, if we try to avoid bandwidth replication, it may not be efficient in terms of number of servers used. So to show that with an example, consider there is a subscriber, and the satisfaction metric is defined in such a way that either selecting Bob alone meets the satisfaction of subscriber, or selecting Bieber and Gaga together meets the satisfaction of the subscriber. So to meet the satisfaction of the subscriber, we basically have two choices. And suppose we also have two servers with their occupied capacity in the gray, shown in gray, and the available capacity shown in white. And it's in such a way that Bob does not fit into any of these existing servers. If you have to allocate, if you have to select Bob to meet the satisfaction, then we may have to deploy a third server. But
are you somehow assuming that all of Bob's load is carried by one server?
Yes.
Why are you assuming that?
Sorry, all of Bob's load for this subscriber.
Just for this?
Just this subscriber, yeah.
Okay, so that's a tiny. If he only gets 5 requests a slot, that's a very tiny load, right? So I guess Bob's load for everybody might be a lot, but for only one subscriber, it's going to be very small, right?
So Bob's load for every subscriber can be divided.
Okay.
So the smallest granularity we are looking at is the topic subscriber pair.
Okay.
So in this example, I'm saying that Bob and this subscriber load cannot be fit into any of the existing servers.
Okay, but just to get the scale right, but typically we have millions or billions of subscriber topic pairs, right? But they're all very small. So the load imposed by Bob's subscription to this particular subscriber is very, very tiny. Is that right? Millions of them, but each individually is
each individual is very tiny, yes. But it doesn't mean that you can always allocate to existing servers. So it depends on what's available. It's always possible that there's not enough capacity.
Like one more drop, that might overflow the pipe.
Yeah.
Okay.
And also there are topics which are generating way too many events. These are not significant number of topics, but in the workload analysis we saw that there are very few topics which generate thousands of events every hour. Because this also depends on music activities and so on, and many things. So in this case, if we select Bieber and Gaga, who are relatively cheaper topics or smaller load, fits into existing servers, but together they have higher bandwidth cost. But selecting Bob has a lower total bandwidth cost, but if we have to select Bob, then we may have to allocate a new server.
I'm still not getting the answer to this question. If we're talking about drops here, why would you, if your bucket is already so close to full that you have to care about how big the drop is, surely it's just time to get another bucket. Why would you want to optimize,
Well, yeah, the bucket's 99.99% full.
If you're really that close, that one subscriber topic pair is going to generate a few events per hour.
In practice, we are not talking about one topic subscriber pair, right? It's an algorithm which is running, and when do you decide? So it's 99.9% or 90%, or when do you decide that we start allocating a new server?
Wasn't the latency going to matter more?
Sorry?
Okay, never mind.
It's just about throughput or latency as well?
We are not considering latency here. I mean, these are social interaction events, and at least from the Spotify perspective, latency is not critical. These are not critical set of events we are talking about. So we formulated this problem again for a given topic subscriber pairs and their event rates and a binary satisfaction metric. the objective was to compute the minimum cost required to meet the satisfaction of all the subscribers. And the cost depends on number of servers and the total bandwidth consumption. And if we are given a pricing model from, let's say, Amazon, EC2 pricing model, then we strive to minimize the total cost, total monetary cost. And unfortunately, this problem is also NP-hard. And we do the reduction from partitioning problem. And we stick to heuristic solutions here as well. So we solve the problem by dividing it into two stages. In the first stage, we assume there is a single server with infinite capacity and try to select as many topic subscriber pairs in such a way that the total cost is minimized and meet the satisfaction of all the subscribers. So if we have an optimal solution for this problem, this is the absolute minimum cost that is required to meet the satisfaction of all the subscribers. And in the second stage, we simply distribute this load. And the second stage is more interesting part. When we look at it, it actually looks like a bin packing problem where we are given a set of bins and items, and we're required to find a packing for the bins which minimizes the number of bins. But one problem with the bin packing solutions is that its goal is to minimize the number of bins, but it doesn't consider the bandwidth overhead I talked about by introduced by the replication of the publication events across the servers. So to address this, we propose a customized version of bin packing solution where we consider the bandwidth overhead introduced by the replication of publications into account. So to give you an example, there are 2 topics here and 3 subscribers. Each topic subscriber pair is a box, and the subscribers belonging to the same topic are in the same color. And the servers have a certain occupied capacity and certain available capacity. And if we just follow the first fit bin packing, which is most common bin packing solution, we allocate the topic subscriber pairs to the existing servers. And now you can see that both subscribers of both topics are split between the 2 existing servers, which means you have to replicate the events belonging to these topics to both of these servers. And this is the bandwidth overhead I'm talking about. This is especially true in Spotify case where they replicate publications from all topics to all servers, which is a significant amount of inter-server bandwidth they are dealing with. So they could actually use this solution to do a better allocation and avoid the bandwidth replication. Yes.
So you said you were using the Amazon pricing. Does Amazon actually charge for bandwidth within the data center?
Not within the data center.
So why is there any benefit with minimizing it, or what's the benefit of?
So there is no inter-server bandwidth cost, but even uploading the events to the Amazon cloud has a bandwidth cost. And also I talked about...
You upload each one independently to each server? Or you're assuming you upload it once and then distribute it internally to the servers running this?
Yeah, you can upload it once and distribute it internally.
Okay, so why is the first FFBP not work for that then?
So yeah, when we looked at this solution, it was not just for cloud setting, it was also for...
You're assuming an Amazon pricing model. You're assuming one where there's an internal cost of bandwidth as well as the cost of the VMs.
Yeah.
Okay.
One more thing is, if it is across data centers, then there is a cost.
Okay, so you're assuming that each VM is now running in a different data center?
It's possible that they are running in the different data centers as well.
Why would you do that?
So the users are distributed across several countries, and the subscribers are connected to whatever data center which is nearest to them, or in terms of load balancing, also they're distributed across.
It's a service where latency wasn't an issue, right?
Yeah.
So why wouldn't you just co-locate them if it's going to keep prices down?
It's not just, okay, the latency is an issue for, let's say, music streaming, but not for publication. And also load balancing is another issue. So the first optimization we introduced in our solution is grouping of topics. Instead of looking at each topic subscriber pair separately, we can actually group them according to the topics. Sure. And allocate the groups of topics together. By doing this, we are achieving two things. One thing is we are trying to avoid splitting the subscribers of a topic as much as possible. And at the same time, it also speeds up the algorithm by, instead of looking at millions of topic subscriber pairs, we are now looking at only individual topics. So this avoids splitting of subscribers to some extent, but it's probably still not enough. So instead we actually introduce more optimizations where we order the topics in the decreasing order of the cost, and consider the most expensive topics first, and also consider the most available servers first, and allocate them to those most available servers. So intuitively, it's a good match for expensive topics to most available servers first, and in principle, it avoids splitting of subscribers across different servers. So I'll briefly move on to, sorry? Yeah. So basically we show with Spotify and Twitter traces that we can have cost benefits, especially when we use Amazon pricing model in terms of number of servers, number of VMs, and the total bandwidth cost. I'll skip the main results and just jumping to conclusions. In this work, we looked into large-scale social messaging pub-sub systems for large-scale social messaging and various challenges it poses. And we looked into novel satisfaction metrics to address the scale. We saw various versions of the problem where to maximize the number of satisfied users or maximizing the satisfaction, these are hard problems, and we provide efficient heuristics to solve. And finally, we also provide a cost-effective resource allocation for data center and cloud settings, and we actually show that there are benefits of using this solution. With this, I conclude, and thank you for your attention.
Thanks, Vinay.